Yeah, so we'll continue to talk about how database works, right? Just to refresh our memory about what we are talking about. In the middle, we always have our database system, okay? And on the right-hand side, you have you as a user who actually interacts with the database by issuing different SQL queries. And whenever you are issuing a SQL query, what's going to happen, I think you already know pretty well, is database going to store your relation as a whole bunch of files on your hard drive, at least in a pretty traditional architecture, is going to do that. Whenever you have this SQL query here, what's going to happen is the system going to bring this piece of information all the way from the hard drive to the main memory and back to you as a user. So before Easter, we have been talking about essentially the right-hand side, how to interact with the database system. So, and starting last week, we start to actually try to open up this box, try to understand how that database system actually do that for you. So essentially, we talk about this pretty traditional classic architecture. So in the bottom, you have a whole bunch of files stored on your hard drive. At the top, you have your SQL query as input, and output is a relation. And like many computer systems, a database system will also have a structure layer by layer. Whenever you go up one layer, you start to abstract more of the complexity in the lower layer. So at the bottom, you have a disk manager, try to manage all those files, and also try to interact with the hard drive. And the layer above that is the buffer manager, try to hide the complexity that you have multiple storage in the hierarchy, right? To make sure everything above it has the illusion that everything is already inside memory. And then you have your access method. We talk about, a couple of them in the last lecture. We talk about you can have sequential scan over files, you can have index scan, you have B plus tree, so on and so forth. So there are different ways for you to access information in a relation. And then today we are going to talk about actually more about access method, and then we are going to talk about this layer, operator execution. This is the layer that you start to have not only how to access data, but you start to have even logical operators. For example, a join, right, a selection, right? All those relational algebra operators, like operators, start to appear at this layer. And then at the top layer, you have your query optimizer, which we are going to talk about on Friday. Essentially, giving a SQL query is going to compile that into a relational algebra expression. And at the query optimization layer, it's going to try to find the optimal way of running that SQL query. It will generate what we call a query plan, and then use all the operators provided in the lower layer to actually run it. So this is this 5-layer architecture of a pretty traditional database system. We talk about this manager, right? We talk about the buffer manager, and last time we talked about, just to refresh your memory about what the buffer manager is trying to do, because we are going to use this, right? It's pretty simple, right? You have this in-memory buffer, you have a whole bunch of pages on your hard drive. Whenever you say, okay, so give me the yellow page, right? In this case, what the buffer manager tries to do is try to check whether that page is already inside the buffer or not. If it's inside the buffer, it's going to return it, right? In this case, the yellow page is actually not inside the buffer. So what the buffer manager tries to do is try to evict some of the pages, right, back to the hard drive, and then bring the yellow page, and then serve this request. And we talk about different ways that the buffer manager can actually pick which page to evict when the buffer is full. So for the access method, right, so last time we talked about some of them, right? We talked about that you can do sequential scan of your file, right? So essentially, if you say, so I have a whole bunch of tuples like in this relation, right? So I want to find the tuple whose attribute x equals to y, right? One way to do that is you can do sequential scan, right? Bring me page one by one, and for every single page, you scan all the tuples and you check whether the attribute x equals to y, right? So this is actually one access method that you have on this relation. If you think about the cost of this, right? So one exercise we are going to keep doing in this course is try to count the number of IOs you have from your hard drive to your memory. For this very simple access pattern, right? So what is the cost? Well, when the pages are sequentially allocated, right, on your hard drive, so what you are going to do for one sequential scan of the relation, right, equals to essentially you pay 1 unit of secant rotate. And then if you have d different pages for this relation, you need to pay d units of the transfer time for every single page. When pages are randomly allocated on the hard drive, right, every single time you access a page, you need to pay 1 unit of secant rotate, and you need to pay 1 unit of transfer. If you have d pages in this relation, you end up have something like this. So, and you can do better, right? Last time we talked about another way of accessing information, right? It's by building a B+ tree, right? Which is just a search tree, but not a binary search tree, but M-way search tree, right? It's balanced, right? Every inner node is at least half full, right? So that there are different type of B+ tree. There's a one type of B+ tree called unclustered, right? In this case, inside the leaf node, you are going to store essentially a pointer, like a record ID, the parallel page ID and the slot ID, right, back to the original relation to make sure you know where to find it. Or you can just store all those actual tuples in your leaf node. If you do that, you get a clustered B+ tree. So in this lecture, we are going to talk about another access method. So we have 3 different access methods to actually play with. We have sequential scan, we have B+ tree, we call it hash table, we are going to talk about. And then we start to use them to really try to understand how can we implement different relational algebra operators in the upper layer. How to do selection, how to do projection, aggregation, so on and so forth. Okay, now let's talk about another access method on your relation, which is hash table. So the high-level idea is when you have a B+ tree and you try to find the record, the complexity in number of I/O is always essentially log n. N is number of tuples, right? So that's the depth of the tree. You cannot do better than that. So often the case is already pretty powerful. Okay, and you'll be surprised what you can do with like 100 megabytes of memory, holding the upper layer of the tree, how much you can do with a single I/O. Right? I mean, you can do a couple 100 million tuples without too much problem. But when you have actually more and more tuples, when you have billions or trillions of tuples, the tree could be pretty deep, right? So that is why we are kind of curious about whether we can do better. So hash table is actually one data structure that allows you to actually find the data tuple in constant amount of I/O. The high-level idea is very simple. I have a whole bunch of tuples. For each tuple x, I try to map it in using a hash function h. Essentially, ideally, right? So what we want is for each of the key corresponding to, for example, one data example, I want to make sure if these 2 things are different, key 1 that doesn't equal to T2, like a key 2, we want to make sure that like their hash, right? After applying the hash function to key 1 is going to be different from applying this hash function to T2. So essentially, right, so the hash function is going to comprise this very big space of all the possible tuples into essentially n different slots. Okay, so essentially, right, one way, like this is one example hash function. Right, I have 4 different tuples corresponding to 4 different values of the ages, right, like in the relation. I could map the blue tuple to the 3rd slot, right? I could map this orange tuple to the 1st slot, so on and so forth. So once I do this mapping, right, sometimes I have these 2 different values being hashed into the same slot, and that will happen, right? Because the number of slots I have is actually sometimes smaller than the total number of input, right? So that will happen at some point, right? So there are different ways to deal with that, but that's like right now, just assume you just put them together into the same slot. Okay. After you do this, right, you start to map this pretty big space of all the objects, contains a whole bunch of values, to a much smaller space that you can check whether there exists a data example being hashed in a specific slot or not. So that's a high-level idea. And then within each slot, right, whenever you are mapping a data object to that slot. Within that slot, I'm going to store essentially the record ID of the corresponding tuple, which is the page ID and slot ID point to the original relation. So once you have this, if you scan the hash table, which is the thing after mapping, right, you can actually check, so there exists one data example being hashed to the first slot, and that example, that object has the record ID look like this, and this is how I can find the corresponding record in the relation. So of course, in real world, right, it's going to be more complex than this example. Sometimes you have correlation, right? So it's like have these two different objects being hashed to the same slot, right? To pay attention there, right? So this is a high-level idea what we are trying to do. So once you have this, there are two fundamental questions that we need to understand to actually build this. The first question, right, is how to define the hash function, right? Given an x, how can we map it to a hash value to a slot? And second question is whenever there are two different objects being hashed into the same slot, what should we do? How can we deal with that? So the first question is a pretty deep area, and people have been doing this in the last half a century. So there are simpler, there are kind of hash functions that are simpler, okay? For example, when you have an integer x, right? So very simple way to design a hash function, right, is do a affine transformation, right? Ax plus b mod p, right? Something like that, where p is a prime, right? So this one is going to map any integer, right, to a collection of slots from 0 to p, right? So yeah, so it's kind of a very simple hash function. When you want to hash a string, right, you can do something like this, right? It could be the sum of essentially SI is ASCII of every single character, right? So then you have some function look like this, right? So I mean that allows you to map a string into a whole bunch of buckets or slots, right, in your hash table. So in reality, right, it's very rare people use this. So there's actually a whole bunch of very fancy hash function, right, that you can use in practice, and they have different characteristics about their performance, their throughput, their randomness, all those type of things. Okay. In this course, we are not going to go deep into different hash function. For now, right, just imagine we have a magical layer hash function that given objects and have a very good randomness. Randomly pick a slot, okay, deterministically, but random in distribution to actually map that to a slot. Okay, you can think about that like that hash function as something as simple as kind of the first one. Right? You have integer, you do a affine transformation, then you mod p, something like that. Okay. So what we are going to cover more is how to deal with the cases that two different objects. The given hash function, two different objects being mapped to the same slot. So there's a whole bunch of ways that you can deal with that. There are two families of methods. The first family of method is what people call closed hashing. In this case, you actually already know how many examples that you want to put into the hash table. Another family is called open hashing, where you actually do not know how many objects that you end up have in that hash table. So let's look at the closed hashing first. In this case, whenever you have two different objects being mapped to the same slot, here is assuming I already put the blue one, I put the orange one in the hash table. Now I want to do the third one. In this case, right, so it's going to map to the third slot. What should I do? The high-level idea of the first approach, called linear probe, is to say, yeah, once I know which slot this object belongs to, if the whole thing is full, I'm going to go to the next slot. If the next slot is also full, I go to the next one. Okay? So it's as simple as that. So what happens with the next objects? Yeah, it's mapped to the same slot. It's going to see, yeah, whether I have empty slot here. If no, I go to the next one. Otherwise, I go to the next one. And then whenever you want to find an object, you say, yeah, here's a value. Try to check whether you have an object in this hash table corresponding to that. Then what you are going to do is the same process. You are going to compute the hash value, right, of that object, and you are going to check whether the slot is empty or not. Okay? If the corresponding slot is empty, then it means that this hash table doesn't contain an object with that value. Otherwise, there will be something there. But if that slot is not empty, you will check the content to see whether it's really an object with that value. If it is not, you cannot stop. You need to go to the next slot, because it is entirely possible the object you are looking for is actually in the next slot. You check the next slot whether the object is there, right? You check the next slot until you find the empty slot. If you find an empty slot, then it means the object you are looking for is not there, right? So it's as simple as that. So we can look at some concrete examples. When you go back home, you can also do this exercise by yourself, right? But we can actually try to see how the algorithm actually performs. So this is a hash table with 28 slots. Okay? Let's try to insert some of the value. For example, insert 1, right? So what would happen, right? So in this case, the hash function is a pretty natural hash function, okay? It is the value mode 29, something like that, okay? So in this case, when you insert value 1, what you are going to have, you are going to occupy the second slot, right? You're going to say, yeah, so it's going to be here. Yeah, you put the 1 there, right? So, and then you insert, for example, 5. Then you're going to occupy this slot. This slot is fine, right? When you have 30, it will become interesting. In this case, as you can see, it's corresponding to the second slot, but when that slot is full, it's actually go to the next slot, okay? And then, for example, what would happen if you have 31? So that actually becomes interesting, is when you have 31, when you hash it, right, it's supposed to occupy the third slot, okay? It's going to occupy slot number 2. But because last time I actually inserted 30 in that slot is full, so I cannot do anything. All I need to do is to say, yeah, I want to do the third slot, but it's full, then I go to the next empty one, okay? And you keep doing this. We'll insert 3, right? So you have something similar. You go this one, you go this, right? When you do 2, it's very similar, right? So when you do 2, you wanted to put that in slot number 2. You cannot do that. You go to slot number 3, it's full. You do slot number 4, number 5. All of them are full, so you end up inserting the value 2 into slot number 6. So that's what's actually going to happen. Okay? This is about inserting values into the hash table. It's very simple. Okay? So when you delete stuff, so what can you do? When you actually, just actually insert, delete this here. When you actually delete things, what are you going to do? You are going to compute the hash value, find the right bucket, and then if the bucket is empty, then you do nothing. It means that the object you are trying to find is not in the hash table at all, right? I don't need to delete anything. If that slot is full, then what you're going to see is going to check the actual value in that slot. If that equals to the key you are trying to delete, then you delete it and you return. Okay? So, but there's a problem. Is you cannot just delete it, because this data structure relies on a property of the continuity of values, right? If you just remove that value from the slot, it is entirely possible you are going to break some of the linear probing process where that slot is actually in the middle. So what you need to do when you find the value you want to delete is to delete it and then put a special value to that slot, saying that, okay, this slot used to be full, okay? Now it's not full anymore, but when you do a query for other values, you need to go continue after this slot. So this slot was not empty, so it has some value. I delete it. When you actually do another query, you need to continue to search the next one, okay? So that's also what's going to happen here. Essentially, if you delete number 2, what's going to have is we are going to check this one, continue to check until we find 2, right? We put a special value there called deleted, okay? You cannot just remove the value Otherwise, you are going to have a hole in that continuous range. Okay? That's going to break other queries. Exactly. When you insert another thing, you are going to overwrite that delete thing. Yeah, so that is a slot that's available for you to input other things. Make sense? Okay. So we can say, for example, you delete 3, right? What's going to have? You are going to find this thing, then you are going to replace that with a special value. Okay? It's very easy to see that you cannot just keep this empty because otherwise I cannot find this 5 with linear probing anymore. Okay, makes sense? And then when you try to query this, you'll say, yeah, find the value 5. As you can see, right? So it's going to find this 5. If I just hash it, we want to find, for example, value 9, right? What's going to have is going to probe kind of the slot. If it's empty, I don't find it. If it's not empty, I keep finding, so I keep checking the slot and all the other slots after it until I reach an empty slot. Okay, makes sense? So this is linear probing. Any question? No? Okay. So linear probing is actually pretty powerful. Oh, where's my cursor? So this is actually pretty powerful. Let's try to understand a little bit about the complexity. Okay? So essentially, the way to think about complexity is actually how many slots that I need to check until I can answer a query. So in this case, in the worst case, it's actually pretty slow. I mean, it's the size of the largest cluster. Right? Because every single time I want to query something, I have to find the slot and keep checking until I reach an empty one. In the worst case, when you have a trivial hash function, like hx equals 0, I don't know why you want to use that, but assuming you have that, what you are going to have is all the objects are being mapped to the first slot. And then, in the worst case, when you already inserted n different objects, try to find them, in the worst case, going to take you n different probes on the, in the hash table. Because all of those are going to be clustered together. So the worst case is pretty desperate. Okay? But luckily, we don't, so this is actually just one example. Assuming all these objects being mapped to the first slot, this is a pretty weird data structure for you to do. Okay? So essentially, every single time you insert something, you need to, even the insertion is actually linear in number of objects, in the worst case. But luckily, we are not even living in a world that everything is in the worst case. So beyond the worst case analysis of linear probing is actually very interesting. It started in 1954 and all the way to, for example, like 10 years ago. Okay? So there's a whole bunch of things you can do about complexity. We are not going to go through them. But essentially, once you assume some notion of randomness of your hash function, okay, you are able to prove different levels of complexity beyond the worst case expectation. Okay? So we are not going to go through that. In practice, if you have a reasonably good hash function, which we are not going to define, if you have something reasonable, okay, so essentially what you are going to have is in expectation. For many practical cases, for every single object, we are talking about, for example, 2 different probes or 3 different probes, something like that in expectation. So in practice, it's actually a pretty powerful data structure. If you want to learn more, there's actually a whole course about this, like how to design a hash function, how to do this, right? How to do universal hashing, all the type of things. Okay. So, but we are not going to talk about that in this course. Now let's try to think about like different ways of dealing with this. Another family of method is called open hashing. So here, you actually do not know how many objects, or you do not require to know how many objects that I'm going to have in this hash table. So there are a whole bunch of things you can do here. So we are going to talk about a very simple case. In this case, right, the hello idea is you maintain a linked list within each of the slot and to put all the objects that map to that slot into a chain. Okay? So essentially, when you have the black one, right, you insert that into this slot, it's fun. You do the orange one, right, you put that in the slot. When you do the third one, right, what you are going to do is you're going to put that together with the black one, right? With the blue one, right? You keep doing this, and then this is the data structure, which is the linked list. Okay, you put them one by one. Okay, so this can actually put a whole bunch of data objects into a hash table, and you can continue to make that chain longer, longer, and longer. Okay, so this is another way to deal with this. So the example should be pretty easy to see. But just make sure we are on the same page about the behavior of the algorithm. Let's try to look at some example, right? So here you have a hash table with 13 different slots. When you insert something, right, you just put them into the corresponding slot. Here is fun, right? You have this linked list, like mapped to this one objects. When you do another one, for example, you are going to keep doing this. So this is actually pretty natural, okay? We have this, right? When you have two things in the slot, you have this linked list with two different elements, okay? And then, for example, have this. You keep doing this. Then you have your hash table. So to delete things is also pretty natural. You first find the right slot, and then you go through all the elements in that linked list, and then you remove them if you find the right element. Okay? Here you remove them, right? When you have, for example, delete 3, it's going to delete this thing, right? It's just going to delete it. Okay? It's actually very natural. So when you want to query it, when you, for example, try to find the key equals to 15, you are going to essentially try to find the right slot. Then you go through every single element in the linked list until you find it. Right? Here you actually find it. For example, if you try to query 27, you are not able to find it. Right? You need to go through all the elements in the linked list. Any questions so far about this? Pretty natural, right? Okay. So what is complexity? The complexity is kind of easier to understand here, right? So essentially, how many elements do I need to check before I can answer a query, right? Which is essentially in expectation is how long the chain is, right? Essentially, that's actually if x, so if the hash function hx is uniformly random, right? So yeah, so I mean, as long as your hash table, right, is kind of as big or similar order like as your input, right, your expectation is you only check constant amount of elements every single time you query it. So this is about hash table, okay? It's pretty natural, okay? It's very important that we know this because then we can implement a whole bunch of fancy linear algebra, relational algebra operators, okay? But this is pretty natural, okay? So there are other indexes, right, so that you can do. There are other access methods, right? So recently there's something called learn index, right? You can replace the whole index structure with a machine learning model because if you think about what index is, it's pretty much a mapping that map a predicate to a value, right? So nothing stops you from just replacing the whole thing with a machine learning model and try to see what's happening. I mean, in some cases it actually works, right? So we are not going to go through this, but there are a whole bunch of different access methods that you are able to provide on a single relation. Okay? So now we know 3, sequential scan, B plus tree, and hash table. Okay? That's enough for us to understand the upper layer. But in practice, there's a whole bunch of things that you are able to do. Okay, now we know all 3 different access methods. We can start to go one level up. I really try to think about how can we use all those access methods to implement relational algebra operators. So that brings us to the operator execution layer. In this layer, the job of the system is try to run a relational algebra operators for you. You can do join, can do projection, can do selection, so on and so forth. The interface we are going to provide to the upper layer is essentially this higher level abstraction to access information without interacting with the buffer, without interacting with the disk, without worrying about how to build a B plus tree, how to build a hash table. All of this are done. Okay? You just tell the access method layer, this is the sequence of access that I want in order to implement this relational algebra operator. So now let's look at some of the operators that we want to implement. So first one is very easy. Okay, we want to implement the select operator, which take as input essentially two things. The first one is a relation R, and second is a condition theta. Semantically, what you are going to do is to say, okay, for every single tuple in this relation R, I check whether the condition theta is satisfied or not. If it is satisfied, I'm going to return it, otherwise not. It's as simple as that. So how can we implement this using all the access method, access method we have? There are multiple ways you can do it, right? The first way is pretty easy. I just do a screenshot scan over the heap file. My relation is organized as a heap file. I just do screenshot scan. So in the book, if you read the textbook, there are different type of heap file, right? So we assume it's always clustered, right? Following like in the terminology of the book. Okay. So it's very simple if you think about what's going to happen. You are going to bring pages, right, from the hard drive to the DRAM one by one, and for each one of them, you are going to scan all the tuples and you check for the predicate, right, theta, and then if true, you output the tuple. So what's interesting is really try to understand the cost, because there are so many different ways you can implement the same operator. And from the system perspective, you need to pick for the user the best one to use automatically. Now let's try to do the exercise to understand the I/O cost of this thing. What is the cost? Well, there are multiple components. So let's make some assumption or notation. Assuming this R has R tuples, okay, the cardinality of the set, that many tuples. Those tuples going to be organized into pages or blocks. Okay, let's assume this relation has BR pages. The function B returns the number of pages of that relation. And we are going to count I/O in pages because every single time I read something, I read a page. Okay, so assuming I have a buffer with M pages, I have a buffer. What is the cost of running of executing this relational algebra operator using this screenshot scan type of implementation? Well, you need to read the information, right? To read the information, what do you need? I can screenshot read the information. I can read a page and then scan all the tuple, right? So the I/O cost to read is equal to the number of pages you have of this relation R. It's pretty simple. And then I also need to write out the result. So the cost of that actually depends on, how many tuples I have in my output. It's a selection. Right? I have n tuples in the input. My output might not be n, otherwise there's nothing to select. Right? So there's one very interesting constant, not constant, like a factor called selectivity of this selection. Which is take as input your condition and also this relation, and output essentially the ratio of tuples that are being returned over the total number of tuples that you have. This term is actually have a really crucial impact on the performance, on the speed, or the I/O cost of this operator. The larger this value is, right, the more tuples that you are going to return, right, the more expensive for you to actually write your result back to your hard drive. But anyway, so on Friday, we are going to talk about how to estimate this selectivity. But right now, assume you have that. Okay, alpha times BR give you essentially in expectation the number of pages you need to hold the output. So the total I/O cost of this operator, if you assume read and write are equally expensive, which is not, but let's assume that read and write are equally expensive, is actually the read cost, number of pages in this relation R, plus the write cost, the selectivity, multiplied by number of pages in this relation R. Any questions? Let's try to make sure we're on the same page about this, okay? Yeah. you need to put back the result.
Write it in the output.
Yeah, right back to the hard drive. Yeah. So because you need somewhere to hold the output, right? Yeah. Make sense? Okay. After we get on several of this, there are different ways for you to implement the same operator, okay? By using different access methods. In this case, assume that we already have a B plus tree that constructed on this relation. You can implement this selection operator using index scan if your condition theta satisfies certain format. For example, it's equal or larger than, something like that. So when C or theta, whatever, when the selection condition, right, is one of this, you could actually use a B plus tree to implement this operator, right? So it's actually pretty simple, okay? So assuming there's an unclustered B plus tree, right, for this condition, what we are going to do is, so I'm going to find the right leaf node, and then I'm going to scan this index from the left to the, okay, so if I'm doing equal or less than, I'm going to scan that from the left to the right, okay? If I'm going to say larger than, right, C is that, if the condition is equal or larger than, I'm going to scan that from the left to the right. If the condition is smaller than something, I'm going to scan that from right to the left. But anyway, you identify the leaf node, and then you scan it, okay? And then whenever you find something that satisfies the search condition, you are going to fetch the actual tuple from your heap file, storing the actual information because the index is unclustered in this case, and you fetch them. And then you write it back to the file as output. What is the cost of that? It's getting a little bit more interesting about this. Again, let's assume, right, this is number of tuples, number of pages. Let's assume we have this buffer. And let's assume the buffer is cold. That is, there's nothing in the buffer at this moment, okay? What is the cost of doing this? So the cost can be decomposed into multiple components. The first component of the cost is for you to identify the leaf node, okay? You need to go from the root all the way to the leaf, which equals to the depth of the tree, okay? In the bigger sense, that's log R, okay? Log over how many tuples you have. That's the depth of this tree. And then once you have this, once you identify the leaf node, what you are going to do, is going to scan it, okay? In this case, what is the cost for you to fetch the tuple you want? So first one, how many tuples do I need to fetch, right? The tuple I need to fetch is alpha multiplied by number of tuples I have. That's selectivity, right? That's how many tuples I'm expecting in my output. Because the whole thing is unclustered, in the worst case, for every single tuple I want to fetch, I will incur 1 I/O. Because all the tuples I wanted to fetch could be scattered in this relation, right? Because my B plus tree is not clustered, right? So I don't have control on how the original tuple is being stored on my hard drive. Essentially, in the worst case, for every single tuple in your output, which equals to the number of that equals to alpha times R, for every single tuple I need to fetch, I incur 1 I/O of a page. In the worst case, that's what I need to do, okay? So this is the cost to fetch a tuple. And then you have the cost to actually write things back. In this case, you have the luxury to actually batch those tuples together into a page, and you only write one page only once. Okay? In this case, the cost of writing it is the same as the cost of the previous case, which is the selectivity alpha multiplied by total number of pages of this relation R. Essentially, the total cost in the worst case, okay, which is actually not that, which is actually pretty reasonable, like estimation about the cost of this, is the cost you need to find the leaf, okay, log of R, plus the cost you need to fetch tuples, alpha multiply the number of tuples in this relation, plus the selectivity multiply the number of pages in the relation. Any questions? Any questions about this? It's clear, right? Any questions? Okay, in the exam, you are going to do this exercise by yourself, okay? So make sure you understand this, okay? Perfect. So what would happen if you have a clustered B plus tree? Let's try to think about this together, okay? So what do I need to do? I need to find the leaf node, and then I need to scan the leaf node. But whenever I'm scanning stuff, I have the actual tuple because it's clustered. So I can just return it. I don't need to fetch it, okay? So what is the cost of this? The amount of I/O you need to find the leaf node is the same, okay? And then the only difference is the cost for fetching tuple is actually different. Instead of for every single tuple, I incur a single I/O at the page level, I have the luxury to just scan the leaf node and output tuples, okay? Because they're all together, they're clustered. So the cost I need to fetch tuples equals to the selectivity of this relation, of this operator, multiplied by number of pages I have in this relation instead of number of tuples in this relation, because all of those are together, okay? And then the cost I need to write something back is the same, okay? It's selectivity multiplied by number of pages. If you put them together, it looks like this. What's interesting about the database system is to put these three different things together. Because remember, before Easter, whenever you are writing a SQL query, we have never been through this exercise. It's never your job as a user to tell the database which one to use. The reason database is fascinating is underneath the cover, database is trying to do this exercise automatically for the user. It's trying to estimate, how fast it is for me to read a page, how fast it is for me to write a page, what is the selectivity of this operator, and then whether I have an index here, whether I have a cluster index here, whether it's uncluster or cluster, something like that, and then try to automatically estimate the cost for each of the different ways of running the same operator, and then going to pick the best one for you without the user really worry too much about it. So that is where the database gets the power. You as a user have no idea how database is going to run your SQL query, okay? So later on, when you have this query tree, have a whole bunch of operators put together, the whole thing is very hard. But as you can see, even for a very, very simple operator, which is a selection or this relation, there are multiple ways for you to run it. And then if you put the cost together, it's not immediately clear which one is the best. So there's some very trivial way of doing it. You just scan it, how hard that can be. But that thing is actually, in many cases, might not be that slow. It actually depends on many things. So in practice, right, so when will using an index pay off? Right? So that's one question. Using indexes like B plus tree might not always pay off. When will that pay off? Well, if you look at this cost model, it will pay off when your selectivity, which is alpha, is not too big, right? You want your operator to be really selective, that the number of tuples that you are returning is very small. Otherwise, if you have an unclustered B plus tree, right, the amount of time you need to actually fetch a tuple can very easily kind of be larger than just scan the whole relation, right? Because when your alpha equals to 1, that is, my operator going to return every single tuple in this relation, using unclustered B plus tree is very, very slow because I lose all the locality on my data access. Instead of if you do a screenshot scan, you just scan it, okay? So that is actually one key difference between this. So it's not always clear that using indexes is always good. It's not really clear that using heap file is always slow. It depends on many things. It depends on the relative performance, the speed of sequential access and random access. They are very different, right, in practice. So it depends on selectivity. It depends on whether your index is clustered or not, so on and so forth. So all of these factors, okay, to consider all of this, is the job of your database system to pick automatically for the user, okay, without the user worry too much about it. So about how to estimate selectivity, how to estimate those costs. So that's on Friday, okay? So today we are going to keep talking about those cost model, and on Friday we are going to put them together to talk about query optimization. Okay, so let's take a break, and then we continue in 15 minutes. Okay, so let's continue. And this become actually interesting, right? When we talk about systems, we'll go all the way from the bottom to the top, right? So the first couple layer can look a little bit like boring, right? Because that's actually, so why are we doing this, right? So this is actually a layer you start to see the whole thing become interesting, right? Because of the way that we organize our data, right? Because of the existence of buffer manager, right? You start to see that because of different data structure that we provide to access information on the relation, you start to see even for this very simple operator, right? So you have these different ways for to implement that, right? And you can start to reason about which one is the best, right? You can reason about how can we pick the best one for the user. And then they start to have very hard technical problem, that is, how can we estimate this selectivity, right? Without actually running it. If you think about that, that's very hard, right? So people spend half a century on it, and we are going to talk about that on Friday. But before that, let's continue to talk about different relational algebra operators. There's one operator that's very popular, very powerful, is you can actually sort information in the relation. It's very simple. You have relation R. You give me an attribute A, one column or a collection of columns, right? You'll say, so I just sort all the tuples according to that attribute. So how can we implement this operator? The first one is, if you happen to have a cluster B plus tree on this attribute A, you are done, okay? So the only thing you need to do is to find the first leaf node, you scan it, right? By the definition of the B plus tree, the cluster B plus tree, that will give you kind of an ordered relation, by definition, in a leaf node, okay? But often, you are not that lucky, okay? So if you only have, for example, unclustered B plus tree on this attribute, it could be pretty slow. Why? Because, so I can still scan my leaf node from the left to the right. But the problem is, for every single tuple that I have, potentially, I could have one random access, okay? So that could be, in the worst case, that could be pretty slow. So one thing that we want to understand is, assuming I have this relation R, how can we sort all those tuples on disk? So in the first year, right, I'm sure you learn about this algorithm called quicksort, right? Where are we talking about sorting again in your second year, right? In our scenario, right, so when you are building a database system, your data is on your hard drive. It's actually very different from your previous model that your data inside your main memory. Inside your main memory, your data is byte addressable. Okay? You can actually, every single time read something, you read a cache line, like 256 bytes, something like that. But when we talk about hard drive, right, every single time I read something, we are talking about like a 4 kilobyte block that you are reading, right? So, and now my data is actually on my hard drive, and the thing I cares about is less about how many times my CPU need to compare things, which is actually something you want to optimize for quicksort. Now I want to optimize the amount of data input and output from my hard drive. So given that, if you simply run a quicksort algorithm when your data is stored on your hard drive, that could be really, really slow. I mean, you could try it, right? But it's going to be very slow. So what we are going to do often in database is to have another family of algorithms, not optimizing for number of comparisons you have inside CPU, but try to optimize for I/O on your hard drive. And that family is called the external sort. So here's how we think about it. Assuming your data is organized on your hard drive in n different pages, and assume we have a B-page buffer. Okay? So that is our assumption. So there are multiple cases. The first case is when n, the number of pages, is smaller than b. Okay? That is, your relation actually fit into the buffer. It's smaller. I mean, the relation is not that big. Right? It's on hard drive right now, but I could load the whole thing into my memory. In that case, it's very easy. You load everything from hard drive to the memory. You have one pass sequential scan to load everything. You quick sort, write it back. Okay? It's as simple as that. Okay? What is the cost? Well, the read cost is all the pages in the relation. The write cost is all the pages in the relation. So of course, we are not worried too much about this case. We are actually interested in the second case. That is, when the relation you have is much bigger than your in-memory buffer. Okay? The number of pages, n, is actually larger than the number of pages in your buffer. So what should we do? The intuition is actually pretty clear. That is, if I have a two sorted file, okay? I have file 1, I have file 2. These two files are already sorted, okay, within them. I do not need that many pages for me to combine them together, to merge them. It's actually very easy. Essentially, all I need is a 3-page buffer to actually merge two sorted files. Okay? So what should you do? Yeah, I mean, I will load the first page of file 1 from the hard drive to the buffer. I load the first page of the file 2 to the buffer. I sort them, right? I go through the top 1 in file 1, top 1 in file 2. I compare these two. Yeah, I output the small one, right? So into my output buffer. And then I do, the next one is actually 2, right? So I output the second one. Now my buffer is full. I just flush it out, right? So just flush this out like as a result. I continue to do this, right? So once I continue to do this, I will actually sort the first 2 pages of these 2 files, and then continue to read. And then I read another page from file 1, I read another page from file 2, and I continue to do this, right? In this case, I have 5, right? And then the second one will be 6. And my output buffer is full. I write back my result, right? Yeah, I continue to do this. Once you have done this, you have a sorted file, contains all the information in file 1 and in file 2. If you think about the cost, right? So yeah, so one pass of reading of file 1, one pass of reading of file 2, and one pass of writing of the whole thing. That's your I/O cost. So as you can see, merging 2 sorted files can be pretty easy. That is one intuition. So that actually gave you a very powerful, very simple, and not simple, but pretty intuitive, but really powerful way of sorting an even bigger file. That is, I partition the algorithm into 2 different phases. In the first phase, it's a sorting phase. I partition a very large file into a whole bunch of small chunks. Okay? And each small chunk is small enough that they fit into my buffer, that I can do quick sort on them. Okay? So once I have that, I have a collection of small chunks on my hard drive that within each chunk, they are already sorted. And then in the second phase, I merge them together, okay, using this very simple intuition. And that gives you a very, very powerful algorithm. So here's how to think about it, right? So assuming I have n pages to sort in my file, and I have a very small buffer, like a 3-page buffer, okay? What should I do? Then what I would do is I will think about this. I have a 3-page buffer. I will bring 3 pages from hard drive to memory. Okay? I'm able to hold it because I have 3 pages in my buffer. I bring 3 pages to my buffer, and then quick sort. I sort them. Okay? I just call quick sort, and it's done. Okay? I read them back. I bring the next 3 pages to my buffer, I sort them, I have another one, I sort them. I have a whole bunch of chunks now, okay? Within each chunk, they are sorted. The 3-page chunk that's sorted. And the next step, I will try to merge 2 chunks using this 3-page buffer. We already show how to do it. Then you have a bigger chunk, right? 6-page already sorted, and then continue to do this merge between a pair of chunks. So that's actually give you a very efficient algorithm if you think about it. It's actually not that slow, okay? But with a very small buffer, you are able to do this. The beautiful thing about this, if you think about it, is all the I/O is actually sequential, right? All you are doing here is to sequentially scan your file again, and again. In the first phase, I'm sequentially scanning it. I bring the first 3 page, I bring the second chunk. They're all sequentially stored on my hard drive. When I merge them, it's also pretty much sequential, because within each chunk, I'm scanning from the top to the bottom. I'm not doing any random access. This gives you a very efficient in the I/O sense, okay? And then you can actually try to analyze a more generic case. In general, right, what is the I/O cost of this process? So MS has multiple components. In the sorting phase, what do I need to do? Essentially, I need to read my file once, and then I need to write the whole thing once, right? I bring in a small chunk from my hard drive to the memory. I only do that for like once for 1 page, right? So the read cost in the sorting phase is equals to the size of the relation, n pages. The write cost is also n pages. So what does that provide in the general case when you have B page buffer? It gives you n over B number of chunks, okay? That's how many chunks you have. And then the second phase is a merging phase. So what do you need to do there? Essentially, with a B page buffer, how many chunks you can actually merge, right? So essentially, you can actually merge B minus 1 number of chunks. I mean, you need to keep 1 page for your output. I mean, you cannot get rid of that, okay? So there's 1 page in the B page buffer holding the output. And then for the other B minus 1 pages in the buffer, each one of those pages corresponding to 1 chunk. It's the head of the chunk, okay? So that actually allows you to actually merge B minus 1 number of chunks to produce an even larger sorted chunk using a B page buffer. And then I want to merge all of the n over B number of chunks. How many of those passes do I need to do, right? So the whole thing kind of like a tree, right, with a fan out equals to B minus 1, right? Because every single time I go 1 layer down, I can merge B minus 1 together into a single node, right? So essentially, how many passes of merging do I need to do? It's going to be log B minus 1 n over B. That is how many passes of merging I need to do to merge n over B number of chunks using a B page buffer. For every single pass of merging, what is the cost? You need to read all the chunks once, you need to write all the chunks once, right? So essentially, the total cost of the whole thing, that doesn't look right. Oh, sorry, it's wrong. Yeah. It cannot be like this. This is very desperate. Okay, so total cost of this, right, is these 2 things combined, okay? So in the big O sense, you have this merging thing. Oh, sorry. Yeah, it was right. Sorry. Yeah, it was right, okay? Okay, so you count how many times you need to read and write your file, okay? In the sorting phase, you read and write, like you read is one, you write is one. In the merging phase, your read is a log, your write is a log, okay? And for each one of the passes, you do n pages, okay? So that's why it looks like this. It's a log plus 1 multiplied by the size of your relation. And essentially, if you think about the power of this, if you have a buffer that only have, for example, square root of n number of pages, the whole thing can be done in 2 passes, right? So that is how much I/O that you need. You actually do not need a very big buffer to actually sort a very big file with like 2 passes of I/O. That's the power of this, okay? So that also gives you something that that also tells you, I mean, even if you have a very big buffer, I do not need to use all of them, okay? So all I need is a square root of n number of pages in my buffer, then I'm done. Make sense? Any question about this? No? Yeah?
Can we make use of concurrency when sorting the single pages?
Yeah. Yes, yeah, it's going to look like this, yeah. So in practice, okay, no one do this in practice. I mean, there are a lot of people on the planet, and someone do this, but in real system, okay, when we talk about SQL Server, PostgreSQL is a weird animal, like SQL Server, DB2, for example, Oracle, right? So often people do a more complex version of this. Okay? Is what's going to happen, there's actually one competition about sorting. Okay? Just how can you sort, for example, 100 terabytes of data as fast as possible. And then you can actually introduce different notion of parallelism into this. Right? So as you said, you can solve them in parallel using the CPU better, but you can actually partition this whole thing into different disks. But at the end of the day, you are bounded by the I/O, but it's very easy for you to increase the bandwidth. You just have more hard drives put in more machines, right? So you have this multiple layer of parallelism put together. And this is usually how people sort in a couple hundred terabytes of data. Okay? Every single year, there's a competition. And every single year, the machine gets faster, and the sorting also gets faster. Now have sorting. Any questions? No? Okay. Now let's talk about the holy grail of database, which is join. Because there are so many different ways you can do this thing. And that's actually the reason query optimization is a very, very hard problem, as we will see on Friday. So now let's say we want to do a theta join between these 2 different relations. Okay, I want to theta join between R and S. So what can I do? So there are different strategies, but let's start from the most, not naive, but most natural strategy. Okay, it's called nested loop join. It's very simple. Okay, it's 3 lines of code. For each tuple in R, for each tuple in S, I check whether theta hold. If theta hold, I output, otherwise I do nothing. Okay? It's as simple as that. If you look at this, if you think about the access pattern of this, essentially what you are going to have is you are going to consider you are going to consider this tuple in R. For this tuple, you are going to scan all the tuples in S, and then you check all the pairs. Okay? And then you move on to the second tuple in R. Yeah, then you do another pass of scan in S. This gives you the correct result. And often when your S is very small, it's not that slow, okay? Because S is going to be held inside the buffer. What is the I/O cost of this? Let's try to get on the same page about what this one has, then we can improve it. The cost of this going to depend on how big your buffer is, right? So let's assume we have a 3-page buffer. We have 3 different pages. What do I have? I have 1 page holding the output. I have 1 page holding R. I have 1 page holding S. The cost of this, if you think about it, is going to look like this. On the R side, I have a sequential scan of R. Right? I keep bringing tuples of R into my buffer, page by page. Okay? So I have one term equals to number of pages inside R. And then for each of the tuple of R, I do one pass of sequential scan on S. Right? And that doesn't sound very smart, but that's what the algorithm actually trying to do. You can do better, but that's not the cause of this algorithm. So essentially, I'm going to look at this. Number of pages in R plus number of tuples in R multiplied by number of pages in S. So here, let's ignore the I/O to write the result out. Okay. So to get the result, it's going to look like this. If you look at this cost model, it's already pretty interesting. Because as you can see, the join order actually matters. Whether you are doing R in the outer loop or whether you are doing S in the outer loop actually matters. Even for this very simple algorithm, you start to see this very fundamental factor that's join order for database system. The join order actually matters. Because if you consider S join R, which gives you the same thing, right? If you do S join R, the cost will be look like this. It's going to be number of pages in S plus number of tuples of S multiplied number of pages in R. Right? So in this case, which one does database want to use? Oh, that's a very simple thing to say, right? Essentially, you want to put a smaller relation in the outer loop where you only have a 3-page buffer. Okay? So which one is better depends on how big your buffer is, to be honest. But if you have a 3-page buffer, essentially you want to put this smaller relation to the outer loop. Okay? Make sense? Makes sense, right? Okay. So again, all those decisions will be done by database automatically for you. So just put them into context, okay? So assuming you have a relation with, your relation R has 1,000 pages with 100,000 tuples. Your S has like 500 pages, like 40,000 tuples, for example, right? So this is actually the number of IOs you need for each of these strategies. Okay? So later on, we are going to bring this value to maybe a couple thousand, okay, as you will see. But for this case, okay, we bring 50 million IOs, okay, all the way down to 40 million. Okay? It's pretty significant. As you can see, even by just changing the join order of a join, using the same algorithm, you can be much, much faster. Okay? It's still not fast enough, okay? But it's faster. So essentially, when you have a small kind of buffer, three different pages, you actually want to put the smaller relation in the outer loop. What happens when you have a really big buffer? What will be the cost look like? So assuming we have a big buffer with M is larger than like a number of pages of S plus 2. Okay, one page holding one page holding R, one page holding the output. All the other things can hold the whole S. All right. In this case, when you have this, your I/O cost will be number of pages in R plus number of pages in S. Yeah, because I only need to read S into the buffer, then I'm done. I don't pay I/O anymore. Okay. So in this case, as you can see, when you have a large buffer, you actually want to put a smaller relation in the inner loop because you want to hold that as much as possible. This actually tells you why we really need a database system to do that for the user, not to have a user to do that by themselves. Because to make the right decision, even for this single join operation with this very simple algorithm, to make the decision is not that easy. You need to understand, okay, how big a buffer is, because there are all those other users using the same system. I mean, they might use a whole bunch of memory. Maybe you only have 3-page buffer. Who knows? So in that case, often the user, that a single user using a database system, when multiple users are using it, when they run in millions of transactions every single second, they do not have this global view of the system. It's very hard for them to make a very simple decision like this. That is, should I do R join S or S join R? Because that depends on how many pages in your buffer, depends on how big your relation is, right? Depending on which algorithm to use. That is why that's actually where the power of database system comes from, is to do this automatically for the user. Okay, we can do way better than this. So there's another algorithm, right, called the blocked next loop join, so which look like this. We start to optimize I/O. Essentially, the whole thing looks like this. For I read R, not tuple by tuple, but block by block. I'm going to read the first block of R, and then I'm going to read a block of S. For each of those pair of blocks, I'm going to check essentially all the tuples, right, in those blocks. Right? And for each of those pair of tuples, I check the condition. If it's true, then I output. If you think about the exit pattern of this, what's going to happen is you first read the first chunk of R, holding the buffer, and then you try to join that with the first chunk of S by bringing that first page into the buffer. Then you do that with the second chunk of S. Then you move on, right? So that's actually one pass of scan of S. Then you keep doing this, move on to the second page of R. What is the cost of this? What is the I/O cost of this algorithm? So essentially, for the R side, really nothing changed, right? So I need to sequentially scan R, right? There's nothing changed. But the number of sequential scans you need for the S relation start to decrease. In the previous example, how many paths of scan I need on S? I need a number of tuples, right? So for every single tuple in R, I scan S once. But in this case, for every page of tuples in R, I scan the S once. Okay? So as you can see, the cost model is going to look like this. The number of pages of R plus number of pages in R times number of pages in S. Go back to our previous example, right? So when you have a two relation look like this algorithm gives you something with only 500,000 IOs. That's one orders of magnitude difference between what we have here and what we have in the most natural way of doing joins. So, 2 orders of magnitude, sorry, 2 orders of magnitude. So if you are doing an advanced system lab, I think after 3 or 4 years, you're going to do the master thing. So remember this example. Optimizing system in today's architecture is often about trying to take advantage of different localities. This is about locality, right? Because every single time I'm loading something, I'm using the same thing again, and again to make sure I don't need to load up multiple times, right? So this is try to optimize this thing by taking advantage of the locality of doing joins. So now let's think about the cost model when you have a big buffer, not a 3-page buffer, but some buffer more than 3 pages. What is the I/O cost of this algorithm? Let's think about it together. I have a big buffer. What should I do? I mean, in this case, it's probably going to look something like this. The thing that you can do is by holding a chunk of S into the buffer. You partition S into m-2 pages. Okay? So that is how to think about it. Now I have m-page buffer. I can hold more information. The thing that I can do is to partition this S such that every single partition of S fit into the memory. I don't need to scan that multiple times. For every single chunk, I hold that in memory. And then for every single of this chunk, you run your algorithm. Okay? If you do this, if you think about what is the I/O you have, on the S side, all you need to do is to load the chunk, do the join, and it fits into the buffer, right? So whenever you want to scan an S, there's no I/O, right? So on the S side, all you need to do is to read number of pages of S. That's the first term. And then for each of these partitions, I scan the R once. And that's the algorithm, right? So I scan the R. It's equals to number of pages in R. How many times do I need to do that? It depends on how many chunks I have. How many chunks I have equals the number of pages of S over, m minus 2, because I have an m-page buffer, and 1 page to hold R, and 1 page to hold the output. So it's going to look like this. We will have a very big buffer. Okay? Essentially, partition S into different chunks. For each chunk, you run the algorithm. So far, so good, right? Now it's getting more interesting because I could also have different access patterns, different access method on a relation. So all of this, as you can see, is what you can do if you can only do sequential scan on a relation. But clearly, we can do more. We could have an index on a relation. In that case, the whole thing becomes a little bit it's still very similar, okay? So it gives you something called index next loop join. You could sequentially scan every single tuple in R. For each of the tuple, if you have an index over S, you can just probe the index, okay? When you find something, you fetch the corresponding S, and you return. So that's something that you can do. The cost model is actually pretty easy, okay? So what's the cost model? I have one sequential scan of R. So that I cannot decrease. That's the number of pages in R. Plus, C is the cost of lookup in the index. Okay? So, and for each tuple in R, I need to pay C because I need to probe the index. So let's just go back to this example, right? So if every single index search give you, for example, 2 IOs in the B plus tree, which is actually crazy if you think about it. Okay, it's almost like a 3-layered B plus tree. Okay, the root is always in the buffer. You have these 2 different layers. It probably give you like 1 million tuples, something like that in S. That's what we can do with 2 IO. Okay, so this one give you, for example, like 200,000 IOs, which is actually much, much smaller than what you have. When you have index, right, sometimes you can do better. There's another thing that people often use in practice called Sophomore Join. Right? So this actually goes pretty close to practice. That is, one intuition is if you want to do equijoin, right? You want to say join R with S, that these 2 attributes are equal. The thing you can do is you can sort R on that attribute, and you can sort S on that attribute. And then you merge them. Okay? In this case, assuming R is sorted and S is sorted, right? You can just bring the first page of R into the buffer, bring the first page of S into the buffer, and you check, right? For the first tuple 1 and 2, they are not equal. They don't match. Then you move on, right? So, and then you throw the 1 away. They'll check 4, right? There's no match, right? You throw the 2 away, right? You keep doing this until you find a match. 4 and 4 is great. Right, then you output that in the output buffer, you find the match. Continue reading this, right? Keep throwing those away, continue reading this, right? So, you can see the algorithm, right? This is probably the most fancy animation I know how to do in PowerPoint. Keep doing this, right? So, and then at the end of the day, when you scan these 2 different tuples, right, like 2 different relations, you get your join result. So what is the cost of this? This sounds like a very expensive algorithm, but it's actually not. Because the the sorting operator, as we saw, can be implemented in a really efficient way. So the cost of this equals to, for example, R and S are sorted. I had to read R once, I had to read S once. That's what I need to merge them. So I pay that 2 different terms. And then I need to sort R, I need to sort S. So in this case, that's my cost. Any questions? So far, so good, right? I sort them, I merge them, okay? And we can do hash join. Okay? This is also another really close to practice of what people are doing, often in practice. Okay? So it's actually relatively easy. I want to do equijoin. Okay? So what I do is I first build a hash table for R. Okay? Then for each tuple S in relation S, I probe the hash table. Okay? If the hash table slot is empty, then there's no match for sure. If the slot is not empty, assuming you are doing this like kind of just like open hashing, right? So essentially, you actually check every single element with the same hash value. If there's a match, you return. So this one is actually very efficient. So what's going to happen is you decompose this into two different phases. You do R join S. So first phase is you build a hash table. Okay? You actually sequentially scan your R once. For every single tuple, you maintain this in-memory hash table, and you put that into different slots. Okay? You do this. And then in the second phase, when you have this in-memory data structure, you sequentially scan the S relation. And for every single tuple in S, you probe this hash table. For the orange one, you hash it, you see, yeah, whether there's any element in the first slot. If there's something there, you check whether it's really the same value, because it doesn't have to be. There could be multiple objects being mapped to the same slot. You check, yeah, and then if that matches, you output something. If it's mapped to an empty slot, yeah, then you don't output. So I/O cost of this is actually fascinating. Okay, what is the I/O cost in drawing these two different relations? Yeah, I scan R once, I scan S once, and then I'm done. Okay, this is interesting, right? Yeah, this is interesting. And then there's another question. That is, what if my hash table doesn't fit in my memory? That could happen, right? So in that case, there's another algorithm called the Grace hash join, where people have in like 1980, something like that, to do that. The high-level idea is you hash this relation multiple times. Given a very big relation R, whose hash table actually doesn't fit into memory, what you do is you first partition it using one hash function. What you do is you sequential scan this relation R. For every single tuple, you hash it, okay? And you put that in the corresponding partition. You bring this R into different small pieces. And then you also hash this S relation using the same hash function. Because those hash function property is you only need to check these pairwise partitions, right? Because if you are doing the first partition of R and the second partition of S, those values are going to have a different hash value on each one that cannot stick, and there cannot be a match. Okay? You only need to check those pairs. And for each of those pairs, you do our hash join. So this is called Grace hash join, which is actually very fast. You think about the cost, what do you need? For R, you read once, you write once, then you get the partitions, and then you read again for your hash join. For S, it's the same. You read once, you write down the partition, you hash join. Right? Essentially, you pay 3 times the number of pages in R and number of pages in S. And all those I/O are sequential. Okay? It's super fast. Okay? So like on this computer, it's like, I think like 3 gigabytes per second, something like that. Okay? And it's a very old one, actually. So now, when you have all those fancy algorithms, we can start to put them together. Assuming we have a Grace hash join, and assuming we have Sophomore Join, how do they compare with each other? Let's go back to this old example. Okay, we have this R, we have S. Assuming we have 100 pages in my buffer. If you do Sophomore Join, this is the I/O cost. Okay, you read R, read S, you pay like 1,500 pages, and then you do the sorting, which is actually going to be very fast. Essentially, we are talking about like 8,500 I/Os to do this join. If you do the Grace hash join, right, we are talking about, yeah, like 3 times how big your data is, right? So like 4,500 kind of I/Os. So if you assume nothing, okay, if all you want to do is to join these two things, And if you just ignore, if you only care about this in the I/O cost type of thing, you should use the Grace hash join, right? So in this case, it's actually assume a whole bunch of different things. You assume the read is as expensive as write, a whole bunch of things. In database, anything that you are using in practice, PostgreSQL, the cost model is going to be much more complex than what you see here. It's going to distinguish the read, distinguish write, have different parallelism, all those type of things. But the fundamental idea is the same. For every single operator that you want to run, for every single way that database know how to run it, there is that formula to model the I/O, to model computation, to model the overlapping of I/O and the computation. Okay, that's also another thing we will not talk about in this class, but very, very interesting. And then it's going to plug in all the assumptions on the cost for each term and try to estimate which one is the best. So in this case, under this very simplistic cost model, right, under these layers of assumptions, yeah, it seems to be for these two relations, the Grace hash join is the thing to do. So this is the type of exercise the database is going to do for you as a user automatically without you worry about that too much. And also, there might be cases where the Sophomore Join is powerful. For example, sometimes your data is already sorted, and that's not a very weird thing to say. Maybe your data is already sorted. Maybe some relation is already sorted. Maybe you are running a SQL query. Maybe there are other operators also relies on a sorted relation, right? In this case, you can actually reuse the cost of sorting that relation. And also, when you need to deal with, for example, some other predicate, right? For the hash join, you can only do equality check, whether A equals to B, right? Because that's all you need to know, like all you know how to do to probe. For Sophomore join, you can do more, okay? You can do A larger than B, something like that in your join condition. So a whole bunch of things you can do. So essentially, you put all those together, right? So you have a cost model. You also have the type of predicate that we can support. The whole thing is not like domination. It's not like one method is always better than the other one, because there's another dimension, is what type of predicate that you can support. For the most natural thing, right, the next loop join, you can pretty much do whatever predicate you can write down as a C++ code. You can just check arbitrary kind of thing, right? And also for the block next loop join, you don't have too much assumption on the predicate of the join predicate. When we talk about index next loop join, the predicate need to be something that your index can actually support. Okay? But otherwise, I don't know how to probe it. So for B plus tree, you can actually do equality, you can do larger than, smaller than, that type of thing, right? For the hash index, you can only do equality check. For the Sophomore join, right, you can do equality, right? In your join condition, you can compare, right? You can say RA is smaller than SB, something like this, right? For the hash join, you can only do this kind of equality thing. So as you can see, these are the constraints, right? Given a SQL query, what's going to happen? Is the system going to check, okay, for this operator, I'm able to do this subset of things. And then for each of those in the subset, it's going to estimate the cost and then pick the best one for you to use. So this is only for a single operator. 2 days later, on Friday, we are going to say, if you give me a tree of operators, how can I make the decision? As you can imagine, that thing is super, super hard, okay? Because it's already hard enough for a single operator. Okay, so this is about join. So in the last 1 minute, there's one thing I want you to remember, is when people talk about join, people always, not always, but people might often think it is a solved problem. I mean, we have been working on that for half a century, right? What's left? So join is a very hard problem. Okay, that's what I want you to remember. Here we talk about join, kind of two relations. But even you have three different, like you have a three-way join, the whole thing is actually pretty hard. if you think about what we are trying to do here, an alternative way to think about relational database is to think about the whole thing as a graph. When you have this type of join, right? So the relation R, right, storing the edges between these different type of objects, right? So S store another type, T store another type, for example. In this case, doing this three-way join is essentially trying to find all the triangles in the graph. That's actually a very hard problem. Because if you join these two different things in a pairwise way, you join R and S, then you join the result with T, right? If you do that, the worst case complexity is always going to be n squared, where n equals the number of edges in the graph. Because in the worst case, you always have the output is going to be equal to n squared. Right? I have n tuples in R, n tuples in S. In the worst case, what I have n squared tuples in the output. But the theory will tell you you do not have that many triangles. You cannot have that many triangles in graph. So how to close this gap? How to have this worst case or beyond worst case optimal join when you have multiple of this is actually something people are working on in actually this decade. It's not like 5 decades ago. It's like this decade, people start to actually close this gap. And this is for a three-way join. Okay? So how to do join really well is super hard. Okay? But in this course, we talk about this two-way join, which is kind of easier to do. Okay, so that's all for today. On Friday, we are going to talk about the top layer. Okay, we are almost done. We are talking about the top layer query optimization. Okay, I'll see you on Friday.